gave the homework 3, but all the problems of homework 3 will there be on the exam? Is it tailor made for the exam or not?
No,
Okay.
some of the problems in homework 3 are, so the relativity portion, I will just ask like somewhat basic things, like let's say, let me open homework problem 3.
And also many of the book problems are also not, I mean, beyond the question of the syllabus of this exam, correct?
That is correct. So some of
Yes.
this I will actually uh, cover in the next exam.
Okay.
So let me actually, maybe I can just tell uh,
Yes,
what
that
I
is
have in the exam, for example, from the syllabus. Just a sec. Uh, Homework 3. Okay, yeah. Right. So, for example, question 1, question 2, right? So can come in the exam, like transformations of E and B can come in exams. So these are just basic 4 vectors. So I won't ask you things about radiation, relativistic radiation in the exam, but I will ask you things like 4 vectors, little bit on Lorenz transformations, things like aberration, this forward beaming thing. I won't ask much about the applications, because I don't think we have done, I mean, you have done these homework problems yet, which are like from Ribicki and Lightman. So 4.1. So things that I can actually ask are things like how is acceleration transformed from one inertial frame to other. But not like great details of astrophysical applications. I will actually have just simple Lorentz transformations, a little bit of how E and B transform, but not the applications. So this is basically what I am thinking of as split. So just like basics of relativity, basics of Lorentz transformations, basics of how E and B transform, not the applications to astrophysics. That we can cover later. Okay, so is this sort of clear?
Yes, sir. Thank you.
Okay, so yeah, more conceptual stuff and little simple mathematical stuff I can ask, but not extremely sophisticated.
And sir, it will also be good if you could come on Friday, so we can, if we have some doubts, we can ask
Sure,
you.
I will. I can be there on Friday in the interaction session. Okay. Okay then. So you can see my screen, right? Or not? Oh, you can.
No.
No. Okay, I haven't. Okay. Now you can see the screen. So yeah, I was actually looking at homework problem 3. I thought it was being shared, but it's okay. So like, for example, question number 1 is fine. Question number 2 about beaming, right? How theta prime are related. This stuff is fine. I mean, question number 3 is like a little bit more mathematical, so I won't really have it. So the questions will be more on concepts and not so much mathematical rigor will be desired, or will be required actually. And then among the homework problems in the book, some of them are which are sort of simple in the sense of are related to Lorenz transformations and aberrations and so on will be in the material, but not really sophisticated astrophysical applications. Okay.
Yes, thank you, sir.
Okay. But the whole of previous homework problem set will be there, which is homework problem set 2. But that, that also had a lot of tedious mathematical questions. I won't be asking those. Right. So, for example, I won't be asking things like this one, number 6, number 7. They are like, and even number 8. Okay. But the others, which are more about polarization, scattering, experimental measurements of polarization, all those are fine. This is fine, right? So no, this is application of relativity, question number 1. So relativistic kinematics and relativistic kinematics will be asked. So the things like omega comma k is a 4 vector, how does it transform? These things will be asked. Okay, good. So now that this is out of the way, let's finish whatever remains of relativity from this portion. And again, as I said, there will be a change of gears from more physics of fast-moving radiating particles to applications to astrophysics, starting from the next class. Okay, so let's get started. So just to refresh what we did in the last class, which was slightly long in the material, I did not want to end it abruptly because I would have to do this material again. So let's recall what we did. Right. We did this, right? So we considered these quantity. Oh, just a sec, let me choose the correct pen size. Right, so we considered these things like dp emitted by d omega in the lab frame, and we related this. How is it related to the emitted power in the particle rest frame, right? The whole program was that we knew the formulae in the particle rest frame, and then we used the properties of how various things like angles, theta and solid angle, they transform from one frame to other, right? So this is easy to calculate, right? In the rest frame, things are easy to calculate. You can use Larmor formula and so on. But this is what you measure. So we had to relate these two, and that is what we were doing in the previous class. So for example, we considered these, right? So we considered this how mu, right? Mu equals cos theta, how mu and mu prime are related to the particle velocity. So these are angle transformations, right? We had things like mu equals mu prime plus beta by 1 plus beta mu prime, right? So how does cos theta, this angle between the direction of photons and the direction of particle motion, how does that change from the rest frame? So primed are always rest frame of the particle to the lab frame, unprimed. And related concepts. So we consider these two special cases, right? So if you have acceleration of the particle, so this is the direction of acceleration, and so if this is the direction of the acceleration in particle rest frame, right, you emit like this dipole radiation pattern. So this is in the frame S prime, particle rest frame. But So and the particle is moving in this. So this is the direction of velocity of the particle as well. So we actually showed that, mathematically, that the radiated power is almost all forward beamed, and the angle of this relative to the particle motion direction is of order 1 by gamma, if beta is almost approaching 1. Okay, so this is a parallel not equal to 0, but a perp, acceleration perpendicular to the particle velocity is 0. The other case we considered was when the acceleration is actually in the direction of the velocity. Sorry, this is the rest frame. It's symmetrical. So this is the direction of acceleration, and this again is the direction of velocity. In this case, you get a pattern like it's all totally forward beamed, and there's a very little going in the back to this angle is of order 1 by gamma, right? Except that here for theta, so this is the lab frame, this is the particle frame, except that at theta is equal to 0, you get the maximum. Here for theta equal to 0, you got 0 because the acceleration was along the direction of particle motion. So if n hat is along acceleration, right? We know that this gives you 0 radiation from just the dipole formula. So all this frame transformation does is it sort of distorts this beam and makes it forward beamed in both cases. Okay. So these are actually very, very important. Don't just sort of get lost in the mathematics. This concept of forward beaming and aberration is very, very important. Okay, so for example, if you have an observer, so if you have like isotropic distribution of stars, right? If some observer is actually moving towards this uniform distribution because the lights are forward beamed, preferentially, what you will see is you'll see excess in the direction of motion, right? So the excess will be much more if the velocity is high, approaching c. But even when velocity is like few hundred kilometer per second, for example, for the solar system, for example, right? So it's sort of moving at few hundred kilometer per second. So you see this in reality. If you count the number of sources which are supposed to be isotropically distributed, you count more in the direction of motion. Similarly, the CMB has this dipole anisotropy, that the CMB temperature is higher towards the direction of motion of the Earth, right? So all these are actually effects because of aberration, that light is not, the light does not travel isotropically in a frame in which particle is moving. Okay, so these things have actually very important consequences. Okay, so this is really from the previous class. So now we'll get started with the last portion of this chapter 4. So invariant phase, space, volume. So the whole program here was actually to have these useful quantities which are Lorenz invariant. So it turns out that the phase space volume, so dV, right, this is equal to d3p d3x. right? So this is volume in phase space. So you have, you know, let's just consider x and p. Forget about the other direction. So this, if you consider like a small volume in phase space, right? So this, right? So you can actually you sometimes deal with things like a distribution function such that d3p, d3x is number of particles in this phase space volume, right? So so this phase space volume is very, very important for a lot of considerations, because if you recall, our I knew the specific intensity that was a primary variable in radiative transfer was also closely related to F. You consider these rays which have some distribution in angle which corresponds to distribution in momentum, and we consider this small volume or area which sort of corresponded to spatial uh, spatial spread. So it turns out that this is Lorenz invariant. In other words, dV is equal to dV prime, uh, which is equal to d3p prime, d3x prime. So this phase space volume, if you look at it from a Lorenz boosted frame, it is the same. That's the consequence of this. So let's see how we can sort of motivate this. Again, remember the two frames. We have frame S and we have frame S prime. Right, so we can actually consider S prime as a particle rest frame. So you have some spread of particles, but it's sort of like uh, some particles are going in this direction, in this direction. So there is a little spread of particle velocities, right? So, but the average velocity is 0. So in the S prime, there is no bulk velocity of particles in frame S prime, but this is moving with some velocity v. Okay, let's see. Okay, we know that. So right, so what is d3x? d3x is nothing but dx, dy, dz, right? The volume, the infinitesimal volume in space. So this, if this is the x direction, right? So the boost is in the x direction. Then we know that dx is equal to dx prime by gamma, right? This is just Lorenz contraction, right? The length is contracted in a moving frame. So this was the rest frame. So right, so the phase space volume, let's just consider symbolically some phase space volume like this. Because of this motion in the x direction, it will be compressed in the x direction, right, by this factor. Okay. So, but in the transverse directions, right? So we know that t comma x, ct comma x is 4 vector, and we know that the transverse components do not change. So dy dz equals dy prime dz prime, right? Because the transverse components of a 4 vector are invariant. So the volume part, dx dy dz equals 1 by gamma dx prime dy prime dz prime. So this is the spatial part of the phase space volume. What about the momentum part? Similarly, right, energy and momentum is a 4 vector, right? So dpy dpz is equal to dp y prime dp z prime. So the transverse momentum does not change. Okay, so what about px? Let's consider, right, so this is energy momentum, this is nothing but gamma m naught c squared, and p is gamma mv or mu. This is this 4 vector, the energy momentum 4 vector. So in the particle rest frame in which the particles are moving, are not moving at a bulk velocity, what do we have? So let's see.
Sir, I think that's C by C.
What?
The four in a momentum 4 vector. I think the first component is zeroth component is E by C.
E by C, sorry, yes, you're right. Yeah, they have to have the same dimensions. Yeah, let me correct this. Yes. Okay. So since we are in the, there is no bulk motion in frame S prime, what is the value of, right? So in frame S prime, that is E prime by C comma P prime, what is that? That is equal to gamma U prime m naught C comma gamma U prime m U prime. Right, so this U prime is the, we are actually considering a small spread in the velocities, right? So this E prime 0, or sorry, just a sec, or P prime 0, which is nothing but, so P prime 0, the zeroth component is gamma U prime m naught C, right? And what I'm saying is there is a small spread in U prime. So this is nothing but 1 minus U prime squared by C squared minus a half m naught C, right? So zeroth component of this 4 vector, and I'm saying that U prime is much less than C. So this is like m naught C 1 plus order U prime squared by C squared, right? So this is actually small. So this is to linear order, it's a constant. So there is some spread in U prime, but it is quadratic in U prime, right? So we are considering particles which are in this frame, they have some spread in x velocity. Okay, so right, so this is so let's actually write just a sec. Let's just write the Lorenz transformation of px. Let me create some space. Okay. So so dpx is equal to gamma dp x prime plus beta dp prime 0, right? I'm just sort of writing the x transformation, and so this beta is the particle velocity, the velocity between these two frames. It is not the same as U prime, right? So this is beta, this V is equal to beta C. This is not the same as U prime. U prime was the spread in velocity in the frame S prime. So U prime magnitude was much smaller than C. So so this is okay. So this quantity is actually of order U prime square, which we can take to be 0 because it's sort of small. So the spread in x momentum in the lab frame is equal to gamma times spread in the particle rest frame. So you see the Px dpy dpz is equal to gamma dpx prime dpy prime dpz prime. So this is the momentum part. This was the spatial part. This is the momentum part. So you see, if you multiply them out, what you get is dv is equal to this 1 by gamma and this gamma cancel, and you get dv prime. So phase space volume is Lorenz invariant, right? So the subtle part was to notice this, that this is negligible. We are considering only a small spread in particle velocities, in particular x velocities, so that this is small, right? We are taking delta ux, right? We are taking delta ux prime, and ux prime average value is 0, and there is a little spread there. So this gives us this transformation, and we get the phase space volume is a Lorenz invariant. Okay, what about this distribution function, right? We know that this times d3x d3p, this is equal to number of particles in small phase space volume, right? So that's the number of particles in the small phase space volume. A number is a Lorenz invariant, right? You know, if you count the numbers in this frame and sum this x prime p prime frame, right? This, you know, there is a one-to-one correspondence between the boundaries of this volume measured in these two frames. So the particles which are lying in this will also lie in this. So the number is a Lorenz it's a Lorenz invariant, right? If you have, say, a bag, and if you have 5 marble balls in the bag, whatever frame you measure the number, it will be the same. So this is a Lorenz invariant. So that means f, which is equal to number divided by phase space volume, is also Lorenz invariant. Understand? This is the distribution function. So this particle distribution function is a Lorenz invariant. In fact, here we sort of took particles, you know, which had a rest mass, but this actually also applies to massless particles like photons, because, you know, in the end we get this, and this sort of is, we can take the limit of you know, this actually is also valid for photons, although we prove it for massive particles. So basically we actually know how F and the energy density, for example, of radiation are related. So let's see, h nu. So now we are going from particles to photons. So h nu F times p square dp d omega, right? So this is the energy per unit volume. This is equal to u nu omega d omega d nu, right? So this is energy per unit volume per unit frequency per unit solid angle, right? This is the energy density that we introduced, and the same thing actually written in terms of the distribution function, right? F times d omega p square dp. This is the number of photons per unit volume, and this is the energy. So this is energy per unit volume. This left hand side, and the right hand side is also energy per unit volume because this d omega d nu go away. So, and we also know that u nu equals I nu by C from our radiative transfer. So what else do we know? We know that for photons P momentum is equal to h nu by C. So, we have actually done this before. So we see that F is proportional to I nu by nu cube. Right, because this P squared dP will give you nu cube. There is another nu here, so but there is also one d nu here which cancels this dP, the nu from there. So I nu by nu cube is proportional to F, and there are like proportionality constant only has constant. So basically, this is a Lorenz invariant. Right, because I argued that F is a Lorenz invariant, so that means that I nu by nu cube is equal to I nu prime by nu prime cube, right? So this quantity I nu divided by nu cube in whatever frame you measure should be the same because it's a Lorenz invariant, and we know that nu is equal to nu prime 1 plus beta this is just the Doppler formula, right? So we can actually write so I nu by nu cube or just a second, let me write it slightly differently. I nu is equal to nu by nu prime cube, which is gamma prime 1 plus beta mu prime cube I nu prime, right? So this is actually similar to these formula. If you recall, we had these dP d omega radiation in the lab frame, and how does it relate to dP radiation by d omega in the prime frame. So these are actually analogous, right? This is done in the language of radiative transfer. This is done in the language of classical E&M. I mean, they're not the same, but they are related, right? Do you see this connection? I mean, there were these formulae, these factors appearing in these formulae that we considered, right? In these that we did in the last class. This is the radiative transfer way of seeing similar things. And there is there is a one-to-one correspondence between these two. Okay, so this is actually important that this, right? I nu by nu cube is a Lorenz invariant. What about other quantities that appear in the radiative transfer equations? Say, for example, di nu by d tau nu is equal to minus I nu plus S nu, right? If this equation holds in all the frames, then if radiative transfer equation is covariant, basically it's the same form in all Lorenz frames, then right, these two quantities, and in fact these three quantities, all should transform in the same way under Lorenz transformations. You see that, right? Whenever you write some equation, if the form of the equation is valid in different frames, then each of the terms in the equation which are added should transform in the same way. So that means S nu by nu cube is also a Lorenz invariant. Do you see the argument? The source function is a Lorenz invariant. What about the optical depth? This sort of transforms like I nu. So basically we also know that tau nu is Lorenz invariant, right? Because you know, I nu and d I nu transform in the same way under Lorenz transformation. So tau nu better be a Lorenz invariant for this equation to be valid across Lorenz frames. And this is also easy to see, right? We know that e to the minus tau nu. What is the interpretation of e to the minus tau nu? Is that basically this is the right, if you have a column of absorbers, right, and if you have like some I naught here, after passing through this column of absorbers, only e to the minus tau nu photons will escape, right? So this is again counting. So you have some n photons here, out of them only n times e to the minus tau nu appear. So the ratio of what comes out and what goes in is just a ratio, right? And it has to be a Lorenz invariant. So it also makes sense that this equation gives you that tau nu is a Lorenz invariant. So this is other radiative transfer concept. What about things like alpha nu? So we can actually write this as right. So what about alpha nu? So let's actually just consider so let's actually consider some beam of light at some angle theta. Okay, and so this is the lab frame, and you know this is some slab through which this light ray is going, and this is some length L. Now this is the lab frame, frame S. Now you consider a frame which is frame S prime, the rest frame. So you know in this frame, this material which is absorbing is moving with some velocity. So if you go to the particle S frame, right, so you have the situation. I mean, this L remains L because motion is perpendicular to this direction. So this L prime is equal to L because the transverse dimensions don't change, but this angle theta becomes angle theta prime. Okay, and so let's see. So what is tau? So what is tau along this beam path? Tau is equal to alpha nu times L divided by sine theta, right? And this is the length, right? This is the length of this L divided by sine theta is this length in this material, right? Along which absorption happens. So we can actually multiply and divide by nu. Okay, so what do we get? We get nu sine theta. So this is right. So we know that for light, for radiation, we know that K omega by C, right? So or and omega is 2 pi nu, 2 pi nu by C. So and so nu sine theta is like K sine theta, right? So nu sine theta, so this is like nu alpha nu L divided by, I mean it's not equal to, it's proportional to K sine theta, which is nothing but K y. So this is the x direction and this is the y direction. But we know that K in the transverse direction is a Lorenz invariant, right? Because omega comma K is a 4 vector. So K along the direction of motion changes, but transverse to the direction of motion does not change. So this is equal to, and we also said that tau is a Lorenz invariant. So this is equal to tau prime. So and ky, so this is nothing but alpha prime, alpha nu prime, nu prime, sorry, is proportional to, sorry, I made a mistake. This is proportionality sign. So this equal to has to be proportional to. Right, and this tau and tau prime are equal because they are just counting the ratio of the particles which are escaping. So this is nu prime, alpha nu prime. Let me also write it in a similar form. So nu prime, alpha nu prime. But ky is the same as ky prime because it's the transverse component, and L is equal to Ly prime. So if we compare these two, we can actually cancel these out. So what we have is alpha nu, nu alpha nu is Lorenz invariant, or nu transforms as nu alpha nu transforms as nu inverse. Right, so alpha nu is equal to nu prime by nu alpha nu prime, which is nothing but, so right, we know from here, so nu prime by nu is equal to alpha nu prime divided by gamma 1 plus beta mu prime. Okay, good. What about J nu? So there are other radiative transfer quantities. What about J nu? What about J nu? Let's see. Recall that J nu equals alpha nu S nu from Kirchhoff's law. Right, so if we know how alpha nu and S nu transform, we know how J nu transforms. So this is equal to alpha nu is nothing but alpha nu prime, nu prime by nu, and S nu is equal to S nu prime nu by nu prime cube. So J nu equals nu by nu prime squared J nu prime. Right, so or nu or J nu by nu squared is Lorenz invariant. Right, so I mean, these are the various ways in which quantities in the radiative transfer equations transform, and we can actually also write J nu in the classical form. Right, if we recall, we had dP emitted by d omega. Right, so this is the formula that we derived for the emitted power as measured in lab. Right, we showed that this actually equals so emitted power by a single particle. We did a single particle, dipole formula. What is this given by? This is given by, I'm just writing the formula from the last class. Gamma to the 4, 1 minus beta mu cube dpe prime by d omega prime. So this was the transformation, and we can always write it in terms of mu or mu prime. So this is nothing but gamma squared 1 plus beta mu prime squared dpe by d omega. Right, so there is a relation between mu and mu prime which we have used to write this down. Now this is for a single particle, right? What is J nu? J nu is equal to the number density of the particles. So this is number per unit volume of emitters times this. So this was what? This was erg per second per steradian. Right, so this is correct. Per right, so but we also want per unit frequency, so we want to do d nu here, so that will become per hertz. So this is how J and power are related. Let's see if we can actually get the same. So this is based on radiative transfer. Let's see if we can get the same from this classical E&M treatment. Sorry, this is cube. This is gamma square beta. So this actually just is a consequence of this equation that we motivated last time, which is just a sec. I'm actually trying to see this relation between mu and mu prime. Just a sec. This one, gamma times 1 plus beta mu prime is equal to 1 by gamma times 1 minus beta mu. See, this is exactly the aberration formula. If you recall, there was this theta to the theta prime. So this is stuff that I may ask in exam. It's simple things. How does a direction change if you go from one frame to other? Just mu was cos theta. So this is what we are using to go from here to here. So 1 minus beta mu 1 by gamma, so the cube, so that gives you cube here in the numerator, and you divide by 1 by gamma extra, so this is fine. Okay, so what about this one? So let's see, how does the number density go, right? So this is in the lab frame. The number density is higher in the lab frame, right? Because because of Lorenz contraction along the direction of the motion. So this is equal to gamma n prime. If n prime is the number density of emitters in the rest frame of emitters, then gamma n prime is the number density as measured in the moving frame. Okay, this is clear. Times, and this is dp d omega formula, which is gamma squared 1 plus beta mu prime cube dpe prime by d omega prime. And then we have d nu is nothing but we'll use the frequency transformation. So this is equal to 1 by gamma nu prime plus beta sorry, just a sec. Gamma times 1 plus beta prime d nu prime. Right? This is how d nu and d nu prime are related. This is just the Lorenz transformation from lab to the rest frame. Right. So if you go from nu to nu prime, there is a 1 minus beta mu. Otherwise, it's this. So this is how your frequency goes. So this guy, this is nothing but j nu prime, right? So what do we get? We get, so this gamma and this gamma can get cancelled, and this will make it nu squared. So what we have is j nu equals gamma 1 plus beta mu prime squared j nu prime, which is nothing but nu by nu prime squared j nu prime, which is nothing but this expression, right? That j nu by nu squared is a Lorenz invariant. Is this clear? So the steps involved were this, like there was a single particle limit, then you multiply by number density of emitters, and you have to be careful about what are the units of this. So we get this. Is this okay? Okay, good. So this is all I had on on the relativistic treatment. So now let me actually briefly tell about what are we going to do next. So this is the end of chapter 4 in the book. So then we'll actually, so for the rest remaining, like 40% of the course, what are the topics remaining? What are these? So we will actually do free emission and absorption, of course. Whenever we do emission, we also will do absorption. They are related by Kirchhoff's law. So free emission, also known as Bremsstrahl law, which is a German name for breaking radiation. So we'll do this, which is chapter 5 in the book. Then we'll do synchrotron radiation, which is chapter 6 in the book. After this, we'll do Compton scattering, Compton and inverse Compton processes, which is chapter 7. And after that, we will do a little bit of plasma effects, plasma propagation, things like rotation measure, dispersion measure. And at the end, we'll do a little bit of atomic physics, modeling of a line broadening mechanisms. So this is the sort of roadmap. And we are sort of at the halfway little more than a halfway mark. So physics is sort of done. We'll be using some of these results later on. Right, so let's see. So the first, yeah, so the, and then yeah. So this will be the plasma propagation effects, and then we'll have some of line profiles, some more detailed modeling of line profiles. So this is sort of the plan. So Bremsstrahlung is the first thing that we'll do starting from the next class. So I think I don't want to start that today itself, but I can actually tell, what is Bremsstrahlung. So Bremsstrahlung is a thermal radiation mechanism. So if you recall our definition of a thermal radiation, so let's see. Strahlung. Or free emission. So in case of say a hydrogen atom, we have a proton and these are energy levels of electrons, right? So if you have a electron here and it jumps from, say, this is n equals to 2 level, this is n equals 1 level, right? So electron jumps from n equals 3 to n equals to 2 level, right? And it sort of emits a photon. This is called spontaneous emission, and this actually is an H alpha line. So in this case, right, the energy of the photon is just the difference between the energy levels 3 and 2, right? So in the spectrum of the radiation, right, the line profile for this will be sharply peaked, right? The emission and absorption will be sharply peaked at this nu naught, right? So this is just line emission. We did a little bit of this previously. What about free emission? So this is also called bound emission. Why is this bound? Can someone make a guess?
Because the electron is finally coming to, means it is bounded to the nucleus.
That's correct. So before emission and after emission, in both cases, the electron is bound to the proton. That's why it's bound, and it has a very specific line, very narrow line. This is bound. Free is basically this situation. Suppose you have a proton and an electron, right? Electron collides with the proton, it gets sort of bent. So there is, this electron which is far away, which has moved. So there is a little bit of time here, right, during which electron is accelerated, right? So an accelerated charge emits, and this is called free emission or breaking emission because of this, that the electron was not in a bound orbit around this positive charge. It was free, and after acceleration it's also free. So that's why free or magnet or Bremsstrahlung or breaking radiation because this electron has been decelerated by protons. So this has been braked by the protons, as in when we apply brakes to a cycle in that way. So this is called braking radiation for that reason. So free emission, like emissivity, for example, J nu, is very broad. It's not like a line which corresponds to a very fixed frequency. So J nu versus nu, for example, has a very broad spectrum, even by a single particle. When it accelerates from here to here, it does not give rise to a very sharp frequency feature. So this is like a continuum emission rather than a line. Okay, there's also something called bound free or free bound. So bound free means that you have a free electron which is moving, and when it collides with a proton, it sort of lands up in a bound orbit. So before scattering, this is the situation. After it's this, and this energy jump corresponds to so E free minus E bound, and this will also be a continuum because, right, electron can have any free energy. It's not coming, its initial condition is not in a particular orbit. So this will also give a range of photon energy. It will not produce a line, right? But it will actually have a cutoff because, you know, the free energy. So, you know, this delta E will be the difference between this, right? So if this particle was at rest, so if this was 0, this is just, right? So you will have energy continuum, but this continuum of energy will go only till this, there will be a cutoff, which corresponds to the energy of bound orbit. So, you know, these are free, bound free, and bound transitions, and these are all thermal radiation mechanisms. Thermal. What do you mean by thermal radiation mechanism? Can someone tell us? This is concept from radiative transfer. What is a thermal emitter? S nu is equal to, for a thermal emitter, S nu is equal to thermal emitter need not always be black body, right? But in a thermal emitter, if your optical depth is high, then the thermal emitter should relax to a black body, right? So emission because of thermal processes. So here you have a plasma which has some temperature or energy given by kT. So the photons that are emitted are also, you know, of the same order. So for example, a very popular common source of free emission in astrophysics are clusters of galaxies. So what are clusters of galaxies? So clusters of galaxies are like deep potential wells where you have many galaxies, and this is a deep potential well. And there is a lot of X-ray emitting plasma. So like temperature is like 1 to 10 keV. So at these temperatures, almost all the ions, except for iron, which is a common species, everything is fully ionized. So this is not possible, right? If matter is fully ionized, you cannot have bound transitions. You need some neutrals in which you can have these excitations and de-excitations. So in clusters of galaxies, you get Bremsstrahlung, for example. The other places which give Bremsstrahlung are things called Stromgren spheres, which are ionized bubbles around star-forming regions, around stars. There also you have a thermal ionized plasma. So basically, it should be a plasma which is mostly ionized, which gives rise to Bremsstrahlung. So yeah, so sort of this was like the big picture overview. So in the next class, we will get into more details. Okay.
Yeah, it is always X-rays in means breaking radiation.
Not necessarily, not always, not always. So in this case, the emitting particles were in this X-ray level. So here, for clusters, you get X-rays, but for these Strom spheres are at 10 to the 4 Kelvin, right? So this can never emit X-rays, right? Because you know h nu for thermal emission, h nu is of order kT. So this, so you know, I know this, that you know the spectrum is very flat, and then there is an exponential cutoff. So this is J nu versus nu, for example, emissivity. So this cutoff happens at nu, h nu is of order kT, where kT is the temperature of the plasma, right? So it's sort of like a black body radiation where cutoff happens at around the temperature of the plasma, but the shape is not black body. This is black body with mu squared, right? The flux goes like nu square, and then there is an exponential cutoff. But for thermal radiation, it need not be black body. Only when it becomes optically thick, it's black body. Okay. So these Strom spheres will not emit any X-rays because the plasma temperature is lower. It's also mostly ionized. In clusters, the plasma is much hotter because the potential, you know, it's hot because the gravitational potential of clusters. So basically, this is what happens: GMMP by R. So this is like a virial temperature, right? The depth of the potential well gives the measure of the temperature of this gas. Whereas here in Strom spheres, the plasma is at 10 to the 4 Kelvin because of photoionization. There are the photons from massive stars ionize the surrounding regions. And this gas is at 10 to the 4 Kelvin. Okay, good question. Anything else? We'll actually do bremsstrahlung in more detail later on, but I thought I had some time, so I'll just give you a little bit of a background. Okay. Anything else? No? Okay, then I will actually see you on Friday. Please do come if you have any questions, and do you know, understand all these concepts. So let me turn off the recording, stop recording.